All right, so we've been given this and the fact that we've got positive x and y's, and we've got to make a proof. And the thing about this proof here is there's x squareds and y squareds in there. So I'm going to try a transformation in root xy less than or equal to x plus y on 2, let x transform to x squared and y transform to y squared. Let's see how we go there. We get root of x squared y squared, and we get x squared plus y squared on 2. All right, so we want to get square root on that right-hand side. Oh, on the left side, the square root and the squares undo each other, so I guess we have this. And now we can just square root both sides to get what we want. All right. And because they're all positive numbers, this works. So not a problem. That's fine there. We've proven the first thing. The second one is fourth root of a, b, c, d is less than or equal to square root of a squared plus b squared plus c squared plus d squared. So we're double square rooting here, aren't we? Double square rooting in the end. And we're probably going to use both the inequalities we looked at. All right, let's just see what we've got. We've got root of a, b, c, d, right? Which is the same as root of ab times root of cd. I'll just get an eraser there. It's the times of root of AB times the root of CD. So from straight above, so this would be root of a squared plus b squared on 2 times root of c squared plus d squared on 2 from root xy is less than or equal to root of x squared plus y squared on 2. Okay, that's a good start. Now, in what was the very first one we were given? Root xy is less than or equal to x plus y on 2. Okay, in root xy is less than or equal to x plus y on 2, let x be a squared plus b squared on 2. Hold on, I can say equal, but I like that. And let y be c squared plus d squared on 2. All right, if that's the case, we root a squared plus b squared on 2 times c squared plus d squared on 2 is less than or equal to a squared plus b squared on 2 plus c squared plus d squared on 2 all over 2. So that makes sense because we get our a squared plus b squared plus c squared plus d squared, and it's on 4 on the right-hand side out of that. All right, so that's equal to a squared plus b squared plus c squared plus d squared on 4, which, if you look at what we're trying to prove, that's the right-hand side's all good. But the left-hand side has still got your square root of a squared plus b squared on 2 times c squared plus d squared on 2. So we need to change that back to square root of AB's CD's. And we've shown up here that the square root of ABCD doesn't equal it. It's, and I've got to be careful there in my notation. I hope someone watching this probably picked that up. square root of ABCD is smaller than root A squared plus B squared on 2 times C squared plus D squared on 2. It's even smaller. So if the left side was smaller than the right, if I replace it with the square root of A, B, CD, which is what we had up there, then we end up with that. So I might just give that a number, that equation a number. I'll call it equation 1. So root ABCD is less than or equal to root A squared plus B squared on 2 times root C squared plus D squared on 2, right? That equation there, I might call that equation 1, so that when I go up to here, I can say from equation 1. All right, now we want to square root both sides, which is possible because we've got all positive numbers cranking. And square root both sides. Left was already square rooted, so I need to square root it again. So I've square rooted both sides, and that leaves me with the fact that that's the fourth root on this side, and the square root of A squared plus B squared plus C squared plus D squared on 4. So, yep, that's what they asked us to prove, so job done.